Hello everyone and welcome to another video in the three-phase circuits course. In this video we are going to cover an interesting topic, power factor correction. So what are the outcomes of this video? Once we finish the video we are going to answer the following questions. I presented here the questions based on the industry employers questions or the interview questions. So the questions are: what is meant by low power factor? Why we need power factor correction? How to perform power factor correction? What are the methods of power factor correction? How to design power factor correction, and we're going to have a detailed example. Then we are going to confirm that one using MATLAB SIMULINK. And then we are going to answer at the end this question: what are the consequences if the power factor correction overcorrects the system? So the system becomes more leading than expected. So before answering the questions one by one, let me remind you about the power factor definition. So the power factor is the ratio of the real power in kilowatt used to do useful work to the apparent power or the total power supplied to the circuit. So in equation form, power factor is P over S. So if you look here for this triangle, we have a useful power. So that one is useful power, we call it P. And that one is a magnetic power, so that one is Q. And that one is the total power or apparent power S. So P over S represents the power factor, which is cosine the angle phi. Question number one: what is meant by low power factor? So in the power triangle, we can see here the power factor is P over S, which is cosine phi. Mathematical wise, phi ranges from 0, lower than phi, lower than 90 degrees. As phi goes towards 90 degrees, that one is a low power factor. As phi goes towards 0, so that one is a good power factor. Cosine 90 equals 0, cosine 0 equals 1. So as phi goes towards 0, this means that P is close to S or equals S. As phi goes towards 90, this means that all the power is reactive power. But what is the consequences for the low power factor? What is meant by low power factor physical wise? Let's look here. A low power factor means more current is drawn to deliver the same useful power. So if we have the same P and we change the reactive power, or at that time the apparent power will change, so we have the same P but maybe for lower current. As you improve the power factor, so you have the same useful power for the lower current. So what is the optimum case? As explained, the optimum case is unity power factor system, zero reactive power, active power equals the total power or apparent power. Question number two: why we need power factor correction? Industry employers like to ask these questions in the interviews. So what are the answer or the best answer for that one? A low power factor increases current flow. I explained that one in the previous slide, which leads to higher losses in the system. So correcting the power factor will reduce the current for the same useful power, so we can save energy and improve efficiency. Another point: power factor correction increases system capacity. Can you explain that one? For example, if we have a transformer 500 kilovolt ampere feeding 3 loads. So if we improve the power factor, so with the same transformer 500 kilovolt ampere, we can feed 4 or 5 loads. Or rather than to buy a 500 kilovolt ampere transformer to feed 3 loads, by improving the power factor, we can have another one 300 kilovolt ampere, and that one reduces the cost. Point number 3. Improving the power factor reduces electricity costs. What do you mean by that one? Most utilities classify a power factor below 0.9 as a poor power factor. So improving the power factor is a must. So for example, if you have heavy industry and your power factor is 0.85, so this means that you need to have a penalty. So it is a must to have a power factor correction or power factor compensation to improve the power factor above 0.9 or 0.95. At that time, you are going to reduce the current taken from the source and you are going to reduce the apparent power drawn from the source. Last point: the power factor correction enhances voltage regulation. So what do you mean by voltage regulation? So for example, if you have a synchronous machine generates voltage, so the percentage of voltage regulation will be no load voltage minus full load voltage over V no load. Can you explain more? Assume that this machine is going to generate 1000 volt if the machine is running at no load. When the machine is fully loaded, the voltage drops to 900 volt. So in this case, the voltage regulation is 100 over 1000, and that one equals 10%. And this is due to the high current passed through reactive component, so IXL is going to have a high voltage drop. If we reduce the current due to the power factor correction, so the reactive drop will be reduced and the voltage regulation drops, for example, from 10% to something like 2% or 3%. So in this case, we are going to improve the voltage regulation if we improve the power. Question number 3. How to perform power factor correction? This is another question the interviewers like to ask the candidate, but the answer is so simple. Look for the power triangle here. We have useful power P, reactive power Q, and the apparent power S. So our target is to reduce the VAR amount. The power factor is P over S, and phi equals 10 inverse Q over P. We can write this equation by another way. Q equals P tan phi. So that one is a certain phi. Assume in this triangle we have phi 60 degrees. So the power factor is something like 0.5. Cosine 60 equals 0.5. So what we should do? We are going to add amount of VAR to have a new Q. So once we know the amount of Q new, we can calculate the amount of VAR we should add. It's called Q add here, which equals Q old minus Q new. So for example, you need to improve the power factor from 0.5 to 0.95. So you need to change the angle from 60 degrees to something like 10 or 15 degrees. So that one is old S. So that one is S new. So you have S new, Q new, and the same P. So you can do the same if you like to have a unity power factor by putting Q new equals 0. So Q add equals old Q old, a negative value to that one. Mathematical wise, Q add equals Q old minus Q new, or equals P tan phi old minus tan phi new. So you know any of these values, then you can calculate the amount of Q added. This is our target. From the previous slide, we know that to improve the power factor, we need to add amount of VAR. So the next question is, what are the methods of power factor correction? Or if you like to ask the question by another way, what are the methods of adding amount of VAR to your system? So this is another question that we can ask students or ask the candidates for any interview. That give me different methods to add VAR to your system. So the simple one and the easy one, that's capacitor banks. So that one is the most common type. That we are going to add the capacitor bank to our system, and that one provides a leading reactive power to counterbalance the lagging power factor introduced by inductive loads, something like motors. So that one will be installed in the bus bars or in the panels, main panel, to improve the power factor of the supply. Please note, if we have a motor, the motor will take its useful power and its reactive power. We're not going to improve the motor reactive power itself. So we are going to improve the system power factor, not the motor power factor. If the motor is 0.85 power factor lagging, all the time will be 0.85. But the system will not be 0.85. We can make the system or the power system will be 0.95 power factor lagging by adding the capacitor bank. So compared to other techniques, that one is a cheap, reliable, and low maintenance. But please note, that one is a fixed value. Later on, we can have a variable capacitor bank. The second method is synchronous condenser. In this case, we are going to have a synchronous machine running as a motor without a load and overexcited. In this case, this machine behaves like a capacitor and supplying reactive power. Synchronous machine itself is a separate course, so I'm not going to speak about modes of operation now, but in this case, if we have a synchronous machine running as a motor and overexcited, that one something like a capacitor. It is used in large power stations and places needing dynamic reactive compensation. It has adjustable power factor correction. So compared to the previous case, that one is adjustable, the capacitor bank is fixed value. It is expensive, has high losses, and requires maintenance. The third method, active power factor correction. In this case, we are going to use power electronic devices such as IGBT to adjust the power factor by injecting compensating reactive current. This technique is used in specific loads, modern industry, as it handles varying loads, filter harmonics, and offer precise correction. It's higher cost compared to the capacitor one. The last technique is hybrid, and that one is a combination of capacitor banks and active power filter. Now we arrive to the main question or the main target of this video, how to design power factor correction. And we are going to focus on capacitor banks technique. So we are going to connect the capacitive load across the loads we want to compensate their power factor or across the bus bar feeding these loads. So we can add the capacitor bank as a star or delta connection. As you can see here, we have a pure capacitive load. So the amount of power, active power is 0. So the total power is QC equals 3V phase I phase, where sine 90 equals 1. The angle is 90 degrees in this case. Also, QC equals 3I phase square XC. Definitely that one is a negative value. What's QC? The amount of VAR to be added to the system to compensate the lagging power factor. We calculated that one 4 slides ago. Also, we can use another equation to design these capacitors, where QC equals 3V phase square over XC, and we call that one as a design equation. So we calculated QC before, so we can use that one to calculate XC. So this equation is valid irrespective of the connection, star or delta, where V phase is the phase voltage in star connection, and V phase equals V line in delta connection. From this one, we can calculate XC, where XC equals 3V phase square over QC, and XC equals 1 over omega C. From this one, we can calculate the amount of the capacitance required to compensate our system to a specific power factor. C equals 1 over 2 by FXC. F is a supply frequency. Let us take an example. Example number 5 in this course. Three-phase system shown in the figure. So we already analyzed this system in video number 8 in this course. So we have a supply voltage 220 volt angle 0 phase value feeding 2 loads. Load number 1 is a star load with 28 kilowatt 0.7 power factor lagging, and load number 2 is delta load with 10 kilovar 0.8 power factor lag. So our task is to design delta capacitive load which injects amount of VAR to our system to improve the power factor to 0.98 lagging. So the design should determine the reactive power to be added or to be supplied by the capacitor bank, the value of the capacitors, infraroods, and the reduction in apparent power achieved after installing the capacitors, and we need to calculate the new supply current. So how to solve a problem like this one? We are going to solve the problem in steps. Step number 1, solve the problem without adding the capacitors. And we already did that one in the previous video. What are the results of video number 8? We have stator current around 86 ampere, angle minus 43.23, and the power factor is 0.73 lagging. The power, active power is 41.4 kilowatt. The reactive power is 38.9 kilovar, and the apparent power, total power, is 56.8 kilovolt ampere. Before going to step number 2, please record these values. Step number 2, determine the amount of VAR required. So the new power factor required is 0.98 lagging. So we can calculate the angle corresponding to this power factor. So phi nu equals cosine inverse 0.98 equals 11.5 degrees. So in this case, we have a new triangle, an old triangle. The old triangle is a green one. The new triangle is the blue one. For the green one, we have old VAR equals 38.87 kilovar, that one. And we have the amount of power P equals 41.35 kilowatt, and the amount of S we calculated 56.75 kilovolt ampere. When we are going to have a phi nu, which equals 11.5 degrees, so we have a Q nu, so we need to calculate this one for the same amount of power P. So let's calculate Q nu. Q nu equals P tan phi nu. From this one, we have Q nu equals 8.39 kilovar. So we have this one and we have this one, so we can calculate the amount of VAR should be added to our system. So Q add equals Q old minus Q new equals 30.4 kilovar. So we have this value now. We can calculate it by another way. That's Q add equals P tan phi 1 minus tan phi 2. So we are going to have the same answer, 30.4 kilovar. Step number 3. Determine the required capacitor per phase. So we calculated from step number 2 the amount of VAR required, 30.4 kilovar. So that one equals the amount of QC, or the capacitor is going to add to our system. And we know QC equals 3V phase square over XC. We are going to have a delta connection, so don't forget that the phase voltage of the delta will be the line voltage of the source. So if you can see here, we have VAB is the phase voltage of the delta. And VAB from the source equals 220 root 3. So we can calculate XC in this case because we know QC, which equals Q add, the amount of VAR will be added due to these capacitors. So XC equals 3V phase square over QC. Let's substitute. So XC equals 14.33 ohm per phase. But we know that XC equals 1 over omega C, so we can calculate the amount of capacitors required, 1 over 2 by FXC, and the frequency of the supply is 50 Hz. So in this case, the amount of capacitance required per phase is 222.13 microfarad. Last step number 4. We need to calculate the percentage of reduction in the volt ampere and the new supply current. Now we have a new power triangle where P equals 41.4 kilowatt between old cases and new cases. No change for the active power. But we have new VAR, new Q equals 8.4 kilovolt ampere rack. So we can calculate the apparent power, new apparent. So S nu equals root P square plus Q nu square. If we substitute in that one, we can have S nu equals 42.2 kilovolt ampere. What is the percentage of reduction? S old minus S nu over S old, 56.75 minus 42.2 over 56.75, which equals to 25.6%. So we can increase the system capacity by 25.6%, or we can feed more load from the same transformer. Regarding the current, we know that S equals 3V phase I phase, so we can calculate I supply new, S nu over 3V phase, 42.2 kilovolt ampere over 3 multiplied by 220, the phase voltage. That one gives you 64 ampere angle minus 11.5. So the supply current is reduced from 86 ampere to 64 ampere. We have a reduction by 22 ampere. So that one we're going to save some losses. For example, if we have 1 ohm resistance and we are going to reduce by 22 ampere, this means that we are going to save losses. 3 multiplied by 22 square multiplied by 1, that one in range of 1.45 kilowatt. So it's a big reduction. Now it's time to go to the SIMULINK platform to confirm the results. We are going to solve the problem in 3 cases. Case number 1, we solved it in video number 8 without capacitors. Case number 2, when we are going to add the capacitors as amount of VAR, or we are going to add the capacitors as amount of farad. Let's go! This is the system we simulated in video number 8. This is a source, load number 1, star load, load number 2, delta load. So if we run this model, we are going to check the results. We have here supply current 86 ampere angle minus 43. And we have the power P 41.3 kilowatt, power Q 38.6 kilovar, and the power S is 56.5 kilovolt ampere. Power factor is 0.73. Also, what I need from you that to look for the results of load 1 and load 2. We look for the load number 1. We have a current 60.6 ampere angle minus 45.6, and the power is 28 kilowatt. And the amount of VAR is 28.6 kilovar, and the amount of apparent power is 40 kilovolt ampere. Regarding the load 2, we have line current 25 ampere with angle minus 36.87, phase current 14.6 ampere, angle minus 6.87, and the power P is 13.3 kilowatt, and the power Q is 10 kilovar, and the apparent power is 16.6 kilovolt ampere. So we need to record these values to check when we are going to add the capacitor to this circuit. The loads, current, and power are going to change or not. Let us see. As we can see here, we have the capacitor bank is connected to the same bus bar feeding load number 1 and load number 2. And the capacitor bank block is similar to the load number 2 because it's delta connection as well. So let's look inside the capacitor bank block and see how to build it. So we have here current measurements to measure the line currents, voltage measurements to measure the phase voltage. And if you want to measure the phase current, we are going to add the current measurements here. And then we have the 3 capacitors will be connected to form the delta connection. But we can have 1 block to represent the 3 phase, but at that time we're not going to measure the phase current. From where you got this one? So let's look for the library browser, Simscape, electrical, specialized power system, fundamental blocks, elements. When we scroll down, we are going to find series RLC branch and series RLC load. So if you like to put that one in terms of watt var, so you're going to choose a load one. If you are going to put that one in terms of ohm, Henry, farad, you are going to choose that one. We have a pure capacitance now, so we are going to choose either this one and put for the power P 0, and the positive var will be 0, and we are going to put the negative var value. So let's drag that one and drop it here. We click on that one. We are going to put the voltage here, which is a nominal voltage. Nominal voltage in this case will be the line voltage of the source. Phase voltage for the delta, that one will be 220 root 3. The frequency will be 50 Hertz. The active power should be 0. And the positive bar should be 0, and the negative bar should be the value we are going to add. So let's look for our capacitor. If we click here, so we have the voltage 220 root 3, 50 Hertz, the power active is 0, and the positive var is 0, and the negative var should be added will be 30.4 10 to the power 3 or kilovar. But that one, if we're going to have one three-phase block, we're going to separate them to 3 impedances or 3 loads, so we need to divide by 3. So each one of those, let me move that one to the right, so each one of those we're going to have third of this power, or going to inject to the system amount of var, third of this power. But if we have one three-phase system, we're going to have 30.4 10 to the power 3. Let us run and see what will happen. We have an error. The voltage source block source voltage 220 volt, 50 Hertz cannot be connected in parallel with the capacitive element. So how we are going to solve a problem like this one? We cannot put pure capacitor here. So what we are going to do, I'm going to click on that one. Rather than put the power active 0, I'm going to put it something like 1 watt, as if we have RC circuit, and this will be the internal resistance of the capacitor. I'm going to have here another one, so that one will be 1 watt. The same for the third phase. So let's run now and see what will be the results. We're going to see these are the capacitor measurements. So definitely the capacitor is going to take a current, and there will be amount of var. So the amount of bar will be something like minus 30 kilovolt ampere reactive. And in this case, the power consumed by this capacitance is 3 watt. And that one is expected. But I need to look for load 2 and load 1 results before going to the source. So let's look for load 2. It takes the same current to 25 ampere, angle minus 36.87, and phase current is 14.6 ampere, angle minus 6.872. The power taken by this load is 13.3 kilowatt, 10 kilovar, 16.6 kilovolt ampere. The same answer as if we have no capacitors. So load number 2 takes the same power. For load number 1, going for the results here, we're going to have 60.6 ampere, the same answer as well for the power P, Q, and S. But what about the source? Let's check for the source now. So now the current drops from 86 ampere to 63.8 ampere, with angle minus 11.15 rather than minus 43.02. And the power factor is increased from 0.73 to 0.98. And the power consumed still the same, 41.3 kilowatts, but the amount of var now changed from something like 38 kilovar to 8.2 kilovar. And the amount of S is reduced from 56.5 kilovolt ampere to 42.13 kilovolt ampere. So the power factor correction now is working fine. So the capacitor now is adding amount of var required to the system according to the design. We are going to repeat our simulation, but instead of using in the capacitor bank load, we are going to use a branch. So we are going to click here. So for example, we have RC circuit now. I'm going to put here 0.0001 ohms. That one is the internal resistance. If we put that one 0, we are going to have an error because we cannot connect power supply and capacitor in parallel. And that one's similar to coil and current source in series. So here we cannot connect the capacitor and the source in parallel. So we are going to add a small resistance, as you can see here. And this is a designed value from our calculation for the capacitance, 222.13 microfarad. And that one for each phase. So let's go for our model here, and we're going to run and see what will be the results. Let's check for the capacitor bank. So that one takes from you something like 2 watts, and there's the same amount of var here, minus 30.4. And that one is the amount of added Q or designed Q to be added to the system. Let's go for load number 2. Takes the same current as before and the same power P, Q, and S. Let's go for load number 1. Takes the same current 60 ampere and the same power factor for this load and the same power P, Q, and S. But what about the source? So the main target now is to improve the power factor of the source. So the power factor of the source is improved to 0.98. and the current drops from 86 ampere to 63.8 ampere, and the angle will be minus 11.16 instead of 43.02. The power P is not changed, so 41.3 kilowatt, and the amount of var is dropped to 8.2 kilovar, and the amount of S dropped to 42.13 kilovolt ampere. The same answer we had if we have capacitor as a load, and that one matches 100% the manual calculation or hand calculations. So what do you think if we increase the capacitor more than this value so we can have a unity power factor? I did my calculation, you can check after me. Assume we are going to put that one, and instead of 222.13 microfarad, I'm going to put that one 281 microfarad. Let's run. I'm concerned with the source now. Let's check what is the results. The current is 62.63 ampere with angle almost zero, close to zero. And in this case, as you can see here, the power factor is unity. So the power P is still 41.34, no change for the power. And the total amount of var of the system now is 112, dropped from something like 38.3 or 4 kilovar to 112 var. And the amount of S now is 41.34, which is exactly equivalent to the amount of power P. So P equals S in this case, so the power factor is unity. So you can use your simulation now to design any power factor correction you like. So now it's time to return back to our slides. So before we end our video, we need to answer this question. What are the consequences if the power factor correction overcorrects the system? The system becomes more leading. So someone can say that this is what we want. We're going to add amount of var in our system. So rather than to have a lagging power factor, we can have leading power factor. But the answer is no. That one is harmful to our system. Why? Overvoltage problem. If too much reactive power is supplied and the system operates at a leading power factor, the system voltage can rise above the nominal value. And in this case, we have overvoltage stresses, which affects insulation and protective devices. That one definitely reduces the lifespan and increases the risk of failures. So the main problem is the overvoltage problem. Number 2. Generators and transformers are designed to work close to the unity power factor. So if we have a leading power factor, that one cause stator overheating, poor voltage regulation, and a big problem for the generators, reduce the stability margin. Number 3, resonance risk. Adding more capacitance to the system might interact with the system inductance, which causes resonance. And the consequences of resonance will be overvoltage, excessive currents, harmonic amplification, equipment failure, which threaten the system safety. Number 4, reduced protection sensitivity. Some protection relays, like overcurrent or distance relays, rely on the power factor angle. So having more capacitance or more leading power factor can confuse the protection scheme, which reduces their effectiveness. What will I watch in the next video? In video number 10, we are going to cover unbalanced three-phase systems. See you in the next video.